Hello and welcome to my CH240 Computational Lab Presentation. In part 1, potential energy curves and bond dissociation energies were calculated. In part 2, diatomic molecules and their molecular orbitals were modeled and compared against the molecular orbital diagram. And in part 3, radial functions, radial distribution functions, and real hydrogenic orbitals were modeled and graphically represented and then analyzed. In part 1, the goal was to calculate the potential energy curve of HBr, HCl, and HF. This was done by using the Hartree-Fock method and an SDO-3G base set. Depending on the internuclear distance that was being calculated, a restricted or unrestricted Hartree-Fock calculation was used. In the process, the HOMO and LUMO were identified and the bond dissociation energy was calculated. The method that was used to do all of this was first, ORCA was used to optimize the geometry of the three molecules. These optimized molecules were then imported into Avogadro and the equilibrium bond length was calculated. Using Python, a program was written that would generate ORCA input files for internuclear distances between 0.6 and 5.0 atomic units. The program compared the internuclear distances to the equilibrium bond distance and determined whether to use the restricted Hartree-Fock method or the unrestricted method. If the bond distance was larger than the equilibrium bond distance, the unrestricted calculation was performed. Since RHF uses the same spatial orbitals to account for each electron, it tends to have trouble with electrons that are not paired. Because of this, it is only useful at short distances, as the electrons are close together and hence likely to be paired up. Once long distances are involved, the electrons are further apart and the bond weakens. Because of this, scenarios where the electrons aren't paired and in the same orbital need to be considered. This is what the unrestricted calculation does. So once this comparison was completed, input files with UHF or RHF were created and ran in ORCA. Following that, an Excel file with all the molecules' bond distances and bond energies was created and plotted using Python. After that, the bond dissociation energy was calculated using a formula shown on the next slide. Here we can see the three curves. HCl and HBr show a nice curve with equilibrium bond distances at around 1.25. However, HF shows a rather erratic curve with a bond distance of around 1. This bond distance may be lower due to the much larger electronegativity of fluorine when compared with the other halogens, which can form stronger bonds by attracting the electrons in a bond more tightly. Another useful piece of information that was obtained was the Mulliken charges of the atoms in the molecules. What these charges represent is the loss and gain of electron density by the atoms within the molecule. As can be seen in HF, the fluorine Mulliken charge is negative. This means that it has gained electron density from the hydrogen due to its electronegativity being higher. By looking at HCl and HBr, we can see that they follow the same pattern in relation to their electronegativities. In part 2, homonuclear diatomic molecules C2, N2, O2, and F2 were analyzed. Namely, the molecular 2p orbitals were modeled and their energies compared to a theoretical molecular orbital diagram. The bond distances of these molecules was also considered, as well as the bond distances of the 2- oxygen molecule and the 2+ oxygen molecules. First, the molecular orbitals were analyzed though. Starting with carbon, we can see that orbital 6 is the LUMO, and if we compare it to the molecular orbital diagram in the top right, we can see that orbital 6 corresponds to the sigma G MO, which is colored in blue. By looking at orbital 5, we can also see that it is the HOMO, and when compared with the graph, it corresponds to the pi U bonding orbital. This would also be the case for orbital 4, as they are degenerate. Sigma U star and pi G star antibonding orbitals are not analyzed here as they are out of our analysis range. Following the same principles as for C2, we can look at nitrogen, N2. Nitrogen's orbital 5 and 4 are degenerate and are the pi U bonding orbitals, and orbital 6 is the HOMO and sigma G bonding orbital. Just like for carbon, sigma U star and pi G star antibonding orbitals are not analyzed here as they are out of our analysis range. With oxygen, we have extended our analysis range to 8 molecular orbitals. This leads to orbital 8 being the HOMO and pi G star antibonding orbital, which can be seen in the spin-up orbitals in the bottom right. Orbital 5 is the pi U bonding orbital, and orbital 4 is the sigma G bonding orbital. Oxygen sigma G orbital is lower energy than the pi U orbital, which is different to carbon and nitrogen, and is due to the different electron configuration and the fact that the oxygen bond is weaker than the nitrogen and carbon bonds. Just like in oxygen, the same is seen in fluorine, F2, where orbital 4 is the sigma G bonding orbital, orbital 5 is the pi U orbital, and orbital 8 is the HOMO, as well as the pi G star antibonding orbital. For both O2 and F2, pi G star is within range, which wasn't the case for carbon or nitrogen. However, just like carbon and nitrogen, sigma U star is still outside of our analysis range. Now that we've looked at the molecular orbitals, we can start thinking about the bond distances. So the distances from nitrogen to fluorine were increasing in a rather linear fashion, as it is expected from looking at how strong the bonds are. Nitrogen is a triple bond and so is really short and strong, whereas F2 fluorine is a single bond and so is long and weak. Oxygen is expected to be in the middle due to its double bond nature, and the bond distance as well as the energies and strength supports this prediction. Carbon is the only outlier here, as it forms a triple bond, however it's weaker than nitrogen and oxygen. This is because it has a lot less bonding electrons than both of these molecules. However, its triple bond is still stronger than the F2 single bond. Now we can compare the ionic variants of oxygen and compare them to the normal O2 oxygen molecule. By removing 2 electrons from O2 to form O2 2+, a more stable molecule is made with a shorter bond length. This is because 2 antibonding electrons are removed. By adding 2 electrons to form O2 2-, the molecule becomes less stable, as can be seen with the longer bond length, and this is because 2 antibonding electrons are added. In part 3, Python was used to model the square of the radial functions of 2s and 2p orbitals. By multiplying these squared radial functions by 4πr², the radial distribution function was obtained and represented graphically. If we have a look at the radial functions, we can see that the 2s orbital has a peak below a distance of 1. Meanwhile, the 2p orbital has a peak around 2. Since the Bohr radius is around 0.529 Armstrong, the 2s orbital is more likely to have an electron be found at a distance below the Bohr radius. Another thing that we modeled using Python is the representation of a real hydrogenic 1s orbital, as opposed to a theoretical or assumed one, which is on the left. And just below that, we have the model of the square of this hydrogenic orbital.